should be, yeah, perfect. Okay. Right. Thank you, Professor Kulkarni, and it was an honor to meet Professor Rao today. He has been our inspiration for many, many years. It's not just about an award, but simply seeing him and being excited irrespective of age. It shows how science must be done. Science is not just an occupation. It's supposed to be a passion. Otherwise, new ideas don't come until and unless it works in the background of your mind at all times. And I'm sure our previous speaker, Professor Pulikal Ajayan, is one of such people also who think about science and thinks about how to excel in his ideas to produce the best quality knowledge propagation through science. So with that, actually, there is another advantage of having Ajayan speak before me. He has set the background very nicely, so I will actually not be saying a lot of, probably don't have to say a lot of details. So let's go ahead with it. And my talk today will be on two-dimensional pathways. The reason I say it's a two-dimensional pathway is because 2D materials, which I'm going to tell a little bit more about, is the vehicle of a new generation of technologies, and we believe that this is going to be a strong contender even to silicon, which Professor Ajayan said earlier, and I'm going to give you a few snapshots of areas where this is going to affect in the near future. Okay, so if you want to build new materials and functionalities, it's supposed to be traditionally driven by chemistry, its instrumentation, its progressive engineering, and of course, the micro and nanostructuring. Nanoscale systems naturally bring with it a certain levels of additional science that we should exploit if you are trying to create new materials for betterment of society. Now, if you take a look at the standard progression in various fields, one of the perfect example is the superconductors, in which how superconducting materials have increased its superconducting transition temperature, and that has led to new areas. For example, MRI machines, one example. It has led to new kind of detectors, sensors, which are now going to be used in case of in quantum technologies, for example. And this had been possible because of chemistry, because of new kind of materials engineering. And with progression, we are pushing our boundaries and moving forward with new applications. Wouldn't have been possible if instrumentation had not joined hands with science. For example, we started with, is there some form of, let's see, yeah, until and unless we had nice vacuum chambers, if that had not been converted to molecular beam epitaxy machines, which can give rise to extremely high vacuum and build better semiconductor heterostructures, we wouldn't have had our mobile phones, for example, if there had not been a gallium arsenide power amplifier in it. And high-quality power amplifiers require high-quality evacuation system and deposition systems. Today, we have this machine, which is an EUV machine for ASML, which makes 3 nanometer to 5 nanometer nodes for electronics. So we have moved from this early vacuum chambers to this kind of machines, and that has been possible through instrumentation. So together, material science and instrumentation is driving the pushing forward the realm of technology today. If you take a look at this progression from 1990s all the way, this is what Ajayan was alluding to, how the size of the transistor has reduced with time. For example, over here, I don't know whether you can see it from the back. So from 130 nanometer, the geometric classical scaling era, to today, about 10 nanometer node, to moving towards 5 and 3 nanometer node, where the length of the gate is becoming smaller and smaller. And imagine what electronics can do today was never even imagined about 10 years ago or 15 years ago when we were using it for laptops and computers. For example, tomorrow we have got neuromorphic computing, where we are looking for electronics that's going to mimic the functionalities of a brain. We have got memories of different types, and there are new areas where material science must catch up. We need to make ferroelectrics, we need to make new resistors so that the power dissipation comes down. So that as we push our technological boundaries, the demand on materials are becoming stronger and stronger. And in this context, 2D materials are one of the most emerging areas in global platform. So as I said, we need to have new materials, and new science must come together and join hands and act synergistically. So what are 2D materials? A perfect example, you have got graphite, and graphite is, after all, a layer, billions of layers of what you call graphene, which is a layer of carbon atoms in one, with a thickness of less than 0.3 nanometers. So this is what graphite is composed of, and this graphene is essentially a prototypical example of a 2D material. It's called 2D because it's flat. Okay. Now, the reason why graphene is interesting is because you can remove graphene from its mother compound, which is the graphite, right? And because the interaction between the two layers of graphene is about 1,000 times, 100 to 1,000 times smaller than a standard covalent or ionic compound, for example, the carbon tetrafluoride or the sodium chloride, and so on and so forth. Now, the reason I wanted to say about graphene is because graphene is also an example where new science and new materials engineering match. For example, graphene was discovered experimentally much later, but originally the interesting part of new science of graphene was formulated nearly 75 years ago by Philip Wallace in Canada. And what Philip Wallace did, and I'll not go to too much of detail, he calculated the energy of electrons in graphene and showed and said that in graphene, the electrons do not behave the same way as in most solids, but it moves like a photon or light in a solid material. It doesn't have a mass. Now that was very interesting, and since then there have been a huge number of experimental activities to isolate one layer of graphene, and eventually in 2010 this was discovered or isolated, and that of course led to Nobel Prize in 2010. 2004 it was isolated, 2010 the Nobel Prize was given to Kostya Novoselov and Andrei Geim. Now, the interesting part of graphene at that point of time was you could make a wonderful transistor, a field effect transistor, in which you have a substrate, and on the substrate you use a scotch tape to press on substrate, and then you leave one layer of graphene on it, and then you put electrical contacts, and you can call what you call a field effect transistor device, where you can change the current by applying a gate potential somewhere nearby. What was interesting about graphene? It was very similar to standard silicon MOSFETs that you see or have in your laptops or mobile phones. But in case of graphene, the electrical mobility, the charge could move much faster, more than 1,000 times faster than standard silicon-based devices. What it did is that it immediately allowed us to make very interesting new ultra-fast transistors. Today, graphene is, well, I mean, in principle, can go to a terahertz frequency at which a device can be operated. Why I can do that? Because if you have a transistor, how fast a transistor can work, how quickly, how fast your computer can work, will depend on how fast an electron can move from one end of the transistor to the other end. And in graphene, because the mobility of carriers is so large that it actually can cause extremely fast operational frequencies, which is given by this frequency ft in graphene-based electrical transistors. But then that's not all at all. What we can do today with graphene is way beyond the transistor action alone. Of course, high-frequency transistor is one. Then we have graphene turned out to be one of the fastest, one of the best conductors of heat. So thermal conductivity in graphene is extremely high because of the strong sp2 bonding. As a result, its thermal conductivity is way better than best of the metals, for example, gold, silver, platinum, copper. Because graphene is a single atomic layer, it has got fantastic surface area, which is why it's excellent to store charge, today's electrical vehicles, etc., can benefit from the large surface area that you have in graphene. In addition to that, you wouldn't believe this, but it's true, the graphene is extremely hard. Again, because of the strong carbon-carbon bond. As a result, equivalent thickness, graphene will be 200 times stronger than steel. So which is why many of the technologies which involve ballistics, helmets, where you would like to create anti-ballistic or vests for soldiers, it's a wonderful system to actually explore whether they can perform high-quality protection from bullets and various other defense-related matters. It's nearly 98% transparent. Light can go right through, which is why it's and it's an electrical conductor, which is why graphene can be wonderful as solar panels for transparent electrode applications. And finally, because it's a single atomic layer, it's wonderful to have it as a non-permeable properties, for example, in bottles and various enclosure or packaging industry. So there are a large number of technologies that can come out from this one single material. Science again. So if you look at the evolution of the quality of graphene since its start in 2004, you see the electrical mobility is a perfect parameter which quantifies the material's quality like this, 2D material. So when it first started, the electrical mobility was just about 5 to 10,000 centimeters square per volt second. We discovered or we realized quantum Hall effect, one of the very important effects for which von Klitzing won the Nobel Prize in 1980, or discovered in 1980 and then Nobel Prize in 1984. But then as we started improving the quality of the material, and this is what material challenge comes into play, in 2010, the mobility has increased by about 10 to 100 times. You started getting graphene with mobility 10 times larger than when it started, and we discovered new effects in graphene. For example, the fractional quantum Hall effect came afterwards. Since 2016, the mobility of graphene has been roughly constant. Now it's about close to 100,000 to 1 million. And this regime is a completely different regime. We no longer now talk an electron moving in a device like a straight line anymore. But now we are talking about electrons moving in a completely different manner in an electronic device. For example, in a standard electronic system, if I force electron from one side to the other, it goes in a straight line, mostly, if it's a good electronic device. When you have extremely high quality device now, like graphene does, you no longer have the straight line motion anymore. Electrons now flow inside these electronic devices like a liquid. So you see, we are talking about new science here. Right? We are not talking about standard methods of electron flow anymore, which we have been taught in our schools and colleges for the last decades. We are talking about a whole new regime of electron flow in high-quality electronic materials. And as a result, you start seeing new effects. For example, electrical resistance of graphene can become negative. Electrons can move in a direction that is opposite toward the forces or the voltages applied. So this can lead to a very interesting new applications, terahertz application, very, very fast plasmonic transistors are new technologies that probably are going to be realizable in the future. Turns out that this is the tip of the iceberg. Okay? Graphene was one, but then after 2004, we started understanding the other materials also have very similar properties or similar structure where you can separate them out from the mother compound using a Scotch tape. And these are called 2D materials, that's why. We started having transition metal dichalcogenides. We started having topological insulators. We even have very high quality, high temperature superconductors now, which fall in the same category. Turns out that we have about 1,800 possible compounds that we can generate by just using Scotch tape in the laboratory. So imagine the kind of playground that we have to build new science and new technology in the future. One such example is molybdenum disulfide. I want to tell you what this example is because it's a semiconductor. It's an important material. It's a semiconductor. It's very similar to silicon, slightly better because silicon, this has got a direct, in its individual monolayer, it has got a direct band gap of about 1.8, 1.9 electron volt, which is slightly larger than silicon. But why is it such an interesting material? Because now you can have, this is the band gap of monolayer molybdenum disulfide. You can make transistors. You can make transistors that can perform exactly like silicon. And this is what Professor Ajay was talking about, that now you can switch it off and you can switch it on, and there's a very large change in the electrical conductance that is possible. But there's more to that. Because it's now available at the surface, it's one monolayer of a semiconductor, if you shine light, it conducts electricity, which means now you can drive electrical current by shining photons. And this is essentially the start of 2D optoelectronics, one of the major fields in developing new technology and new science in very large part of the globe. So this is the technological roadmap as far as 2D material is concerned, 2D semiconductor is concerned. This slide I took from IMEC press release. Typically, silicon versus 2D electronics. 2D electronics does have certain key advantages because they're very thin. Some of the bottlenecks in today's miniaturization, for example, the short channel effect, the electrons jumping from one side of the transistor to the other very easily, that can be reduced. We can have other kind of energy efficiency because they're standard miniaturized ones. So if you see, this is where we are, 3 nanometer node. If we are to go farther up, then the exploratory devices include the 2D materials, and they are also tipped to be what we can use in quantum technologies. I'll come to that a little later. So just a bit of history. When 2004, it was graphene that was started in Manchester. In 2011, it was 2D materials, MOS2 in EPFL. Around that time, we had, in the Indian Institute of Science in Bangalore, we were trying to combine the two. Our goal was to, okay, it's a very interesting new 2 materials have come up. One is a semi-metal, graphene, other is a semiconductor, which is molybdenum disulfide. We were asking here, can we combine the two? And do you think once we combine, the combined property will be far better than the 2 material individually? So we were looking for what we call emergence, and that was the source or the motivation behind this. So what we did is that we were starting to talk about what you call van der Waals heterostructures, the atomic Lego. We were trying to create materials which nature by itself doesn't provide. For example, what we could do, and now we can do very regularly, I don't do, my students and group members do very well, you can take materials from different chemical genre and then you put them together in a sequence that you want and building a new material with very, very different properties. Okay? So that's the core strategy that new material science probably is in 2D domain is taking. So this is an example in which you take a material of molybdenum disulfide, you put a graphene, you put a layer of boron nitride, you put a layer of graphene, another one. It's up to you how you want to build this new material. It's kind of like this, okay? Half the body of a tortoise and then duck or whatever, or something like this. You don't get them in nature, but we can make these in the laboratories. So why are we interested in this? It turned out that these are extremely high quality. The functionality-wise, these are amazing. And the same set of material, and this is something which is interesting, same set of materials, by simply combining them in different manner, you can make the best optical detector, you can make a very interesting thermoelectric, you can make a neuromorphic device, and series of applications like that. So this is a strategy or an emulation of functionality that you can do by building a bottom-up assembly of materials. For example, this is graphene. The moment you put graphene on molybdenum disulfide, you shine light, and the current changes. It's a little bit of light current changes by a very large amount. You can make various kinds of devices from here, and even you can make single photon detectors. And this was one of the most interesting outcome, because you can see when we shine light in bunches of photons, each photon will have a very different number of, or a bunch of, or pulse of photon will have number of photons in them, is statistically distributed. by looking at these numbers, by looking at the optoelectronic current in these high sensitivity optoelectronic systems, we can find out how many photons are there in a pulse of photons. So this was very important and probably have a direct application in photonic quantum computing. If you are not interested in quantum, but you are a biologist, then there is another area where you would like to make memories that can mimic a biological synapse, or how we, how a communication between two neurons occur in our brain. Usually there are two key steps. So if you have a brain in which you want to cut two neurons off, then you want to reduce the electrical conductance of the synapse. Or if you want the communication to move from one neuron to the other, you want to create higher conductivity between the two synapses. And most of the times, the way we remember, the way we take decisions, most of our training process of the brain depends on how you have interconnected different neuronal circuitry. So a memory here is what we need today, is something that we can use to train the memory by putting pulses and increasing the conductivity, or putting pulses to reduce the conductivity. So this is called potentiation, where I increase the conductivity by applying pulses, or I can reduce the conductivity by applying negative pulses. So this was a challenge to semiconductor physicists. Can we make memories like this? And now there are huge number of areas in which people are looking for phase change memories, ferroelectric devices, spintronics, and nanowires, organic molecule materials to make such memories. They are usually very challenging to make, because at the end of the day, we have the neurons, there are about 10 to the 13 neurons in our brain, so it needs to be very small and very efficient. So one of the examples that we did was essentially use the same set of material which worked for optoelectronics. We made these kind of neuronal devices where the graphene was on the bottom and the molybdenum disulfide was the top. We essentially made the electrons move back and forth to make memories like this. For example, if you put pulses, we can see the current increases. We put the opposite pulses, other way around, current increases here, and we can make this pulse number go up and down, essentially making potentiation and depression at our own will for a very long time. The advantage of making 2D material as a platform for such memory, if you take a look at the typical energy dissipation for pulse, this is roughly where human brain is, about 10 picojoule per synaptic action. 2D material can offer a very nice solution where the energy dissipation can be much, much lower. I will not be able to finish this without telling the new kid in the block, the new science, and this is what Ajay said a little bit, that is twistronics. So now what we can do is that we can take two materials and put them together. Again, nature doesn't do it for you, but you do it yourself, make them twist against each other a little bit. It has been shown over the last 5 years that this can lead to a whole new range of effects. And for example, superconductivity, this came out of the MIT group about 5 years ago. Now, I'll not go into the detail of this, but we can tell you that superconductivity is not the only thing that is possible. For example, again, we can use the molybdenum disulfide layers and then take two layers of molybdenum disulfide and twist them completely against each other, and we end up getting a new kind of ferroelectric. And this has been recent work from the group. Again, something which is more technical detail, is a new science and having a direct application in form of electronic devices, and we have seen this. Okay, how much time do I have? Girdhar? Wonderful. I would like to spend the last 12 minutes of my talk about a technology roadmap, where I would like to share with you what are the key bottlenecks of developing technology, commercialization aspects, because I'm sure there will be plenty of people who are here to do, who are entrepreneurs, would like to learn about what to do with these new materials. So as far as 2D material is concerned, electronics is one of the key areas. There's no question about it. And And the way the progression has happened, what are the areas we are thinking of is this. So about 2018, roughly, that's where the materials-based scaling has more or less ended. We saw the early figure in which we saw a tapering off of the growth of the number of transistors per unit area in an electronic device. Around 2010, we have started putting 2D material in the stack. It's a purely exploratory stage. It's still probably generations away from a pure 2D-based electronic device, but it started getting into what you call a more than Moore era through heterogeneous integration, where our next stage of electronic devices certainly cannot get rid of silicon. That's not possible. But whether 2D materials can come in as a partner in the integration. There are certain challenges in semiconductor silicon-based era, for example, making CMOS devices with equal P and N doping. So some of those problems can be handled by 2D materials. 2026 or so, we are talking about CMOS plus X era, and in which we are talking about high performance performing, again, coming in with new kind of architectures. Maybe 2026 is an optimistic estimate, but still there's a lot of work coming in. In particular, new type of energy devices and photonic integrated devices probably are going to have 2D material in them as a core element in the structure. We are talking about 2030-ish that will require CMOS probably, or probably 2035, where we will see 2D coming in probably mainstream electronics, as well as quantum computing, neuromorphic computing, and these kind of eras. So this is a rough estimate of what probably we would like to see in the next decade or so. Okay. Before that, there are technologies to build. And some of those technologies do not require the electronic properties per se of just the electronic properties of 2D materials, but they can be built on the other properties, its strength, its surface area, and various other attributes that some of which we talked about. What kind of areas we believe are going to be benefited by this? Again, I don't know whether people over there can see, but there are already application in composites. Because of the strength, because of the non-permeability of two-dimensional materials, composites are becoming a very interesting application in lightweight and high-strength composites. For example, for aircraft bodies, a little bit of graphene in there can actually improve the ability of the strength of the material while reducing the weight. Energy sector is extremely important. We have already fast-charging batteries. We have advanced photovoltaics, flexible perovskite cells. There's a huge number of applications where 2D material is now being very strongly being researched, and there are applications which are available. Data communication, we have got optical fibers, data modulators, where 2D material-based systems are now are being looked for. Electronics, I already talked to you about. Sensors, as finally biomedical technologies in kind of neural interfaces, measuring electric fields that, EEG, for example, MRIs, whether application of 2D materials can help them, are one of the key areas of research and development in today. There are more than 350 to the 2D related company in 2019. This was about 4 years ago. It's increasing, but with new science, it increases far quicker. What are the key challenges? Production. The biggest challenge in 2D is particularly for those applications which require volume infusion, production. Right now, the global capacity of making 2D materials is about 2.5 kiloton per year. The demand is not less because it is too small a quantity to build. Okay, about today's demand is about 300 to 400 ton per year. We would like to take it as and when the new technologies use this. We expect the requirement is about 10 kiloton per year. Okay, it needs standardization. 2D material technologies are not standardized. The materials quality, the device performance require a global standardization strategies. Cost pricing is very important. At the end of the day, if you want to buy a material from the market, you want to buy the lowest cost material that gives the same performance. You don't want to buy something because it has got 2D material in it, right? So what is the global direction of cost? So today the graphene nanoplates which are used, for example, in car tires, you have carbon black. The reason car tires are black is because you have got carbon black in them. But you can have better car tires tomorrow. For example, if you can have graphene in them, you will still be black, but the road resistance will be, and the car tire lifetime will become significantly better. But until and unless we start creating the cost to be significantly smaller than the standard carbon black that you get in the market, and it's not going to happen, for example. As I said, the car tire industry alone, if it is commercialized, will require about 10 kiloton per year of graphene. So where is that volume going to come from? Professor Rajan told a little bit about synthesis using chemicals, exfoliation technique, liquid exfoliation. That's one of the areas, but one has to improve the efficiency of those techniques significantly if you want to make a commercial 2D material-based society. And as I told you, you can see the number of fields: automotive, ink, textiles, concrete, polymer. Imagine this building having 0.3% of graphene. It has been shown by research the concrete life goes up by about 30 to 100% if you have graphene in them, a tiny amount, by 0.3 to 0.4%, which means each building is going to last about, instead of 10 years, about 13 to 14 years. Imagine the social advantage that we are going to get from there. Okay, last couple of slides, I'm nearly done. Because of all the other applications, on one side, there's a new technology in the block, and that's quantum technologies. And 2D material is one of the key areas in quantum technologies that we must look at. There are many, many areas in which, whether you can make electronics, superconductors, topological magnetic materials, quantum communication vehicles, single photon detectors, quantum computing and sensing applications, and another defect-based sensing applications. Quantum technologies are going to be benefited by 2D material science and new science in a critical manner. Because of which, National Quantum Mission, the Indian government has recently started the National Quantum Mission in computing, communication, sensing, and materials. And in the materials, 2D material has been explicitly mentioned. This is one of the areas the government, Indian government, would like to see grow and proliferate with direct application potentials being exercised. Thank you very much for your attention.
Let me coordinate the sequence of questions. Please.
Will the layered electronics be able to replace GPUs that are being used right now? Will they be faster than them? And the second question is, you mentioned about the negative current for graphene. Can you tell me where it's going to be applied for? Is it intended?
Right. So the first question is more application today. TSMC and IMEC, there are key semiconductor companies are trying to replace silicon, or at least gauge the potential of 2D materials for long-term electronic applications as a device. But they are generations away, which means I cannot see this happening before 2035 as a standalone 2D material-based device. But now our wafer scale growth have been more or less identified. There are technical challenges like contact resistance problems, high current problems, so they are being researched on at the industrial level. As far as the negative resistance is concerned, that's extremely recent science. And there are certain applications that have been, for example, terahertz detection, high-speed transistors have been suggested, but they will take much longer.
Yeah, I have a question or comment. You spoke about the 2D heterostructures. These are all done by nanomanipulation. But that's going to be the real bottleneck, right, for large-scale fabrication. So any way out?
Well, I think Ajayan is the right person to talk about it, but there are ways in which you can now synthesize these 2D heterostructures in various manners. You can make them in laterally or vertically. Vertically also it's possible, but certain sequences are more conducive to vertical growth than the others. But there are now several people who are working towards making 2D heterostructures at the wafer scale.
Thank you, Professor, for a wonderful talk. I'm Srinivas. I work for Saint-Gobain, so come from an industry background, and I really appreciate both yours and Professor Ajayan's focus on the manufacturing part of it. A quick question on the translation from early stage development of materials to its application. With your experience over the last number of years, are there any heuristics or indicators that you have developed that where you can back the right horse rather than, I mean, or is the best way just try and fail or till you succeed? Are there any advice that you have?
As far as 2D material is concerned, I can tell you that there are now the horse, you have created all the saddles and everything. We know which are the areas that 2D material will be, paradigm shift in terms of device functionalities. The problem is in producing large quantities at sufficiently low cost. That's the only aspect that requires to be solved. There are many different areas in which strategies that are going to be applied. Now, question is whether we identified the right way to make it. There are promising areas, there are not so promising areas. So I think the moment we have the commercial viability of the material, technology is ready to shoot.
There's one more, last one, please. Take the microphone.
Yeah.
On how 2D standalone devices will only come by 2035. But in terms of integrating with existing CMOS technologies, when you talked about the issues with contact resistance or CMOS compatibility, do you envision a time in which it'll be possible to have both 2D and conventional systems on a chip, or will it only happen when you have a whole other type of technology for just pure standalone 2D devices?
Good question. There are certain applications where are niche applications, where only 2D can do, but silicon cannot. The problem is there are very, very few of them. I mean, one of the probable areas is high sensitivity optoelectronics, could be one of them, and I know there are companies which are making 2D based pixelated cameras, but there are very, very few such things. So for those kind of applications, you do not need to wait for 2D to become as good as silicon in most of the other technological aspects. But if you look at the mainstream technology, silicon or electronics technology industry is concerned, as I said, I mean, I can't see happening before 2035, if not later.
All right, thank you. Thank you, Professor Arindam. No, you're not going.
I already have a lot of things.
No, you should carry this as well.
Okay.
Sir, kindly go to the center. Professor Arindam Ghosh, kindly accept the memento. So with this, you want to say something?
No, I just want to thank the organizers for this honor. So let me close the session by thanking both the speakers. Thank you.
So we'll now break for lunch. So do come back at 2:10. We are as per schedule. There is no delay, which generally happens in a science conference. So please come at 2:10 so that we'll start the deliberations at 2:15, because nano in energy, we have 4 sessions. In fact, 3 sessions, and currents inside disconnected lithium batteries after fast charging. So please enjoy your lunch and do come back at 2:10. Thank you very much. Namaskara. All of you take care.